we'll continue on with section 4.3 about Riemann sums and definite integrals. So let's pop off to where we left off. Let's get off this so I can pop off to where we left off. So we're dealing with this, our theorem, that the definite integral gives you the area of a region. And for this to work, though, we have to be non-negative and continuous on a closed interval. Then the area is going to be this definite integral from a to b of f of x dx. And we said we can find that by taking the limit as the norm approaches 0 of the Riemann sum, which was I equals 1 to n of f of c sub I delta x sub I. So that's kind of this, one way we use this definite integral. So let's give this a try. So we want to find the area between the graph of f of x equals 2x squared plus 3 and the x-axis on the interval negative 2 to 1. And we notice on this one, unlike the other one, since x is squared, always positive, this will be non-negative for all real numbers. So we're cool with that. We can do this definite integral. So that's what you want to do. So take a minute or to see if you can, probably take you a few minutes. Give this one a try on your own. Pause the video. When you think you're ready, pick it back up, and I will work through this with you. So again, we're looking at this integral, definite integral from negative 2 to 1 of 2x squared plus 3 dx. And we're going to do this with our Riemann sums. So the limit as the norm approaches 0 of I equals 1 to n of f of c sub I delta x sub I. Nope, wrong button. And I'm going to again go for regular partitions. So I'm going to make delta x be 1 minus a negative 2 over n, or 3 over n. And I'm going to make my c sub I, again, the same thing I did on that other one. I'm going to make that negative 2 plus 3i over n. It would be so much nicer if I started at 0, wouldn't it? No. Okay, so if we do this, then we can say, yeah, this is a regular partition. We can say definitely this is the same as saying n approaches infinity. We can work this like the problems we did before. So let's just, it's a good, again, some more practice working these problems. So we're doing the limit as n approaches infinity of, here we go, I equals 1 to n of 2 times a negative 2 plus 3i over n squared plus 3. And we take the whole thing times our delta x, 3 over n. Now, yeah, it's just working this out. This is the fun part, isn't it? I'll take out my constant. Let's see, in here I have 2 times, let's square this thing out. So we're going to get 4. 2 is 6 times 2 is minus 12i over n plus 9i squared over n squared plus 3. Let's work this out a little bit more. We got 2 times 4 is 8 plus 3 is 11. 2 times 12, 24 over n, 24i over n. 2 times 9 is 18, I squared over n squared. Choo 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 choo. So n approaches infinity, 3 over n, and let's break these up. So we have the sum of I equals 1 to n of 11. We have 24 over n times the sum I equals 1 to n of I plus 18 over n squared times the sum I equals 1 to n of I squared. So we get 11n, 24 over n times n minus 1 over 2, 18 over n squared times n, that's an n plus 1. I always want to say n minus 1 there for some reason. 2n plus 1 over 6. Just gets uglier and uglier, doesn't it? I'll take out this 2 and I'll take out that n. So I got minus 12n. I got minus 12. Whoa. I don't know how I changed my 3 over n to 3n. And I know you're yelling at me when you're watching this and saying, "What are you doing, Mr. Wilkin?" And it's kind of like, okay, I'm messing up. Okay. So we got minus 12 there. I can take out an n that way, and I can take out 6 that way. So I got 3. So this is going to be where are we at here? Okay. This is 2n squared plus 3n plus 1. We've done this plenty enough times. So we take this as 3 times 2n squared is 6n squared over n. Take 3 times 3n is going to be 9n over n. And 3 times 1 is going to be 3 over n. And yeah, 11n minus 12n is going to be, here's a negative n. Minus 12 plus 6n plus 9 plus 3 over n. Oh, where are we at now here? Now we'll take it times the 3 over n. So we get 3 over n times a negative n is going to be a negative 3. This is going to be minus 36 over n. This is going to be plus 18. That's going to be plus 27 over n. And that's plus 9 over n squared. And when I take the limit, as n approaches infinity, this goes away, this goes away, this goes away, and I ended up with negative 3 plus 18. And I end up with 15. Yeah. That is the joy of doing these definite integrals with the limit of the Riemann sums. Now, it's going to get easier. Just like with derivatives, when we had to do that with the limits, it was a pain to start off doing it with the limits. We're practicing some of those. Sometimes that's what you have to go down and do, but we will learn some other ways, some other shortcuts to do it. And one of those is just using some geometry. Because again, if this is just the area between the curve and the graph, look for opportunities that you can just say, oh, if I'm looking at for 4 dx, that's this function here. I'm looking from 1 to 3. I want this area. That's just a rectangle. That's 4 by 2. That's 8. If I'm looking at this one, x plus 2, we're going from 0 to 3, so at 0 we're here. 1, 2, 3. At 3 we're at 5. We want this area here. We can either use, our trapezoid. That's a nice trapezoid. 1/2 base 1 plus base 2 times the width. So we can say 1/2 of 2 plus 5 times the width of 3 is going to be 1/2 of 21 is going to be 10.5. Or you could make this up as a rectangle. This is 2 by 3 and a triangle. Either way we can do that. You look at this one, square root of 4 minus x squared. That's a semicircle. That looks like that. So we can just go area of a circle is pi r squared, and we're doing 1/2 of it. So when your radius is 2, so that's 1/2 times pi times 2 squared equals 2 pi. Sometimes we can look at them and say, hey, this is just something I can use geometric formulas on. Go ahead and do it. That's one of the nice things with graphing. You can't always do that, but when you can, take advantage of it. Because again, as long as we are continuous and non-negative, this is giving you an area. And if it's a type of a graph that you can look at that and use your geometric skills, your formulas for areas to find the area, go to it. Last thing I want to talk about is some properties with this. First thing, if f of x, if f is defined at x equals a, then the integral from a to a of f of x dx is 0. And if you're integrable on a to b, then the integral from b to a of f of x dx is the opposite of the integral from a to b. So if you're going, it's basically saying if you go backwards, you get the opposite area. You get the opposite value if you go from the other direction. So kind of an opposite idea. It works with a lot of it. The other thing is, if we're looking for the integral from a to b, we can take the integral from a to c and add it to the integral from c to b. Let's do it this way so that doesn't keep on popping on me. You know, these have to be the same. And then we're going from a to b. We can break that up into chunks and add the chunks together, because we're doing this just by this idea of making chunks and adding them all together. So these are some of our nice properties here. We also have our favorites come back. We have the constant multiple rule, just like with limits and with summations and with derivatives. A constant times the function, we can pull the constant out and then do the integral. We have the sum and difference formulas work. The integral of a sum is the sum of the integrals. But you notice when we're doing this, these are the same limits of integration on both of those. So with this one, as opposed to on the previous slide, we don't have different limits here. These are the same. And we can kind of put that together. So let's give this a try. See if you can do these on your own. Pause the video. This is a lot quicker than the last one we did. And then come back to me. For a, the integral from 0 to 7 of f of x. Here we're going to 0 to 4. This is going from 4 to 7. So this is the integral from 0 to 4 of f of x dx, plus the integral from 4 to 7 of f of x dx. So that's just going to be 14 plus 20 is 34. The integral from 7 to 4, notice we just switched the order, is going to be the opposite of the integral from 4 to 7 of f of x dx, which is going to be a negative 20. Go jump down to this one quick, then I'll do C, which is longest here. Integral from 2 to 2 is 0. We know that it's defined at 2 because it's inside this interval, so it has to be defined at every place in there, so we're good. This last one here, we're going to say, well, this is going to be, you can say this is the integral from 0 to 4 of 3f of x dx minus the integral from 0 to 4 of 2g of x dx, which is going to be 3 times the integral from 0 to 4 of f of x dx minus 2 times the integral from 0 to 4 of g of x dx is going to be 3 times 14 minus 2 times 10 is 3. This is going to be 30. 42 minus 20 is 22. Now, the one thing I'm going to say is when I'm looking at your work for doing these, I don't want to see, here's the problem, here's the answer. I want to see you breaking it down and showing me how you're using these properties in order to get that answer. And when I quiz you on it, I will take points off if you're not showing me this breakdown and showing me this understanding of the properties. If you just give me the answer, yeah, you know what, you know how I work, right? So these are these properties. If we know a few, it helps us find others. So the other last thing we want to hit is this, is that integration preserves inequalities. So we're saying right here, f is integrable and non-negative on the closed interval. So it's always going to be bigger than 0. Second thing we're saying is that f and g, if they're both integrable on the closed interval, and g is always bigger than f for every x on that interval, then the integral of g is going to be bigger than the integral of f. And that's that preservation of inequality. If the one function is always bigger than the other, then its integral will be bigger than the integral of the other. So that's kind of that preservation of inequality. So, yeah, this was another long one. A lot of things to talk about. Work on these problems. Work carefully. Make sure you're showing your work as you go through those. Have fun.